Thank you very much, Yuval, for these very nice words. Title of my talk today is It's Time for Secure Operating Systems. Of course, in proper Australian, it should be, it's about bloody time, but I'll leave it to the proper English. This term, It's Time, has actually got a special sort of history in Australia because it was the catch cry of the Labour Party when they won the election in 1972. Over 50 years, and that's also some relevance here. So why? So secure operating systems, people have been trying to do secure operating systems for quite a while. The first well-known one is the PSOS system, which was done at Stanford and SRI, and that was tried to prove the security of an operating system. PSOS stands for provably secure operating system. Precisely specify each module at each system layer, as well as inter-layer state mapping, etc. And they didn't quite succeed. Although some simple illustrative proofs were carried out, it would be incorrect to say that PSOS was proven secure operating system. And that was in the 1970s. And few years later, there was a comparable effort at UCLA. They tried to do similar things to a Unix system, verification of the UCLA security kernel. And that was published in 1980. So a lot of work in the 70s into the 80s. There was also the VAX security kernel, etc. And then there was, after this initial optimism, there was a lot of delusionment, and people basically stopped trying. And by the turn of the century, people had accepted that operating systems are insecure and had some other innovative ideas. For example, the interesting concept that you make an insecure Windows system secure by implanting a rootkit. What could possibly go wrong? Mind boggles anyway. So that was sort of the last century, and I would claim significant step forward was finally achieved in 2009, so 16 years ago. We had some contribution to that, where the SE04 microkernel was designed, built, implemented from scratch and verified. So there was an abstract model, and the C code implementation was formally verified to be correct against this abstract model. So in that sense, the first provably bug-free operating system kernel implementation. Just having a verified abstract model, of course, doesn't mean it's any good. And the initial model actually had some interesting features where you could build a completely a system that the user level could crash at any time because the spec was wrong, basically. And then there was more work done. That was actually not found by proving things about the spec, but by just trying to verify the implementation against it, and there was a mismatch. But then we went on and proved the standard CIA security properties about this model. So in that sense, there's now a pretty strong assurance that the model is actually good. And there was also a proof check constructed to prove that the compiler didn't introduce bugs. So the code that the compiler produced was a refinement of the semantics that was proved about the C implementation, which takes the assumption about the C semantics out of the trusted computing base as well as the compiler, which is nice. And this is done now for 4 different architectures, pretty much all the standard ones around, long song, but anything we care about. And it's, I would claim, still the most comprehensive operating system kernel verification story. There's a few more things, for example, well, the important thing is there's a few other verified OS kernels around now. None of them has capability-based protection. I'll get to that, what that means in a second. And we've also done a complete and sound worst-case execution time analysis on the kernel, although on a dated ARM processor, because we can't do it on the present processors. But we're about to restart that work on Windows 5. There's some limitations which I put up for truth in advertising. And the nice thing is it's all open source, so widely accessible. Who knows what capabilities are, like in the operating system sense? Yeah, about a third of the group. So capabilities go back to Dennis van Hoorn, also in the 70s. They are fine-grained tokens for fine-grained access control. So in a capability-based system, you can only perform an access if you have been given an explicit capability to do that. So, and what that means is we can completely control communication in an SEO4-based system. So two components can communicate if an explicit channel has been provided to them. And if they don't have a channel, they cannot directly communicate. So in this case, the native untrusted can only communicate with this Linux VM via the native trusted component, which can filter requests, etc. So this is really key to reason about information flow and in general security on the top of the system. And anyone who's trying to sell you an operating system that's not capability-based and claims it's a secure kernel, I don't think they're serious about security. You can quote me on that. And very dear to my heart, my motto is security is no excuse for bad performance. We did not sacrifice performance for security. And that was independently established in this paper from 6 years ago, where they looked at various open source microkernels, compared the latency of the core IPC operations, so its latency, so small is good, and found that SEO4 on this x86 platform is about factor 3 faster than Fiasco, about factor 9 faster than Google. Not sure how they do that, takes talent. And they also compared that against the mandatory hardware costs. So what are the minimum operations just to switch context on this processor? And the result is SEO4 is about 25% slower than the bare minimum hardware costs, which tells you, okay, it might be possible to get a few percent faster than SEO4, but not a factor of 2 or so. And we're far away from the others. Like this Google thing has an order of magnitude overhead. As I said, I'm not sure how they do that. Okay, so this is nice. And it's been core for SEO4 being deployed in real-world system. This is a secure communication device that's in daily use in multiple armed forces. In the DARPA HACMS program, we protected autonomous vehicles, air and ground vehicles from cyber attacks. It's been used in satellites. Critical infrastructure protection, there's a new project starting on that one very soon. And as of September, it's actually deployed in electric cars running around in China. This is a new sub-brand of NIO, who also sell in Europe. DARPA was so confident about this thing that they keep rolling out the research vehicles from the HACMS program. And any opportunities, so 2.5 years ago, they brought it to DEF CON and a conference, this Steal This Own challenge. And as the program director tweeted, many tried, none succeeded. So that's really cool, in the sense that, yeah, you can actually use SEO4 to build real-world systems. And so looking at the timeline, original work is now 16 years old, so that's quite a while. And some of the other verification work was done in the next 4 years, so that's also well over 10 years now. Finally open sourced it 11 years ago, and then there came the DARPA HACMS program. So that was quite significant because I said earlier, people tried to do secure operating systems, verifying systems, and then there was this big disillusionment in the 90s. DARPA, for example, had invested a lot in formal methods in his early days, and then got completely turned off. And the HACMS program manager, Kathleen Fisher, had a hard time convincing people that it might be a good idea. And she told me later that when she took the proposal that's gone through the internal processes to her office director to sign off, the director said, this is never going to work, but we are DARPA, we're taking risks. And when we then delivered what we promised for the whole program after 2 of the 3 phases, that generated a complete change in mindset. So finally, people realized, yes, formal methods are actually good for the real world now. And there were follow-up DARPA programs. One of them we've funded under now. And so there's verification was extended to other platform architectures, etc. And as I said, we finally have commercial cars on the road, which is nice because finally something to point to rather than defense projects, which are all hush-hush, etc. So this is sort of nice, but it's actually frustrating because I'm preaching to convert it here. We still don't have secure systems by and large. Some niche products which are really secure thanks to SEL4, but by and large, the world is just as unsafe as it's been, if not worse. And obviously, this is now increasingly exploited by state actors and organized crime, etc. So why 15 years, 16 years after the original SEL4 proof and now 8 years after the successful deployment in real-world vehicles, how do we still not have a secure operating system people can just use? And to me, that's sort of a really disappointing realization. I expected it to be widely used by now, a long time ago, actually. In order to sort of understand what happened there, is we need to first understand what is a microkernel. So microkernel is, my tongue-in-cheek comment is you take an operating system kernel, you take all the easy bits out, and the black molasses that's left, that's a microkernel. A more serious definition is a microkernel contains only operations that need to be executed in kernel mode. Any functionality that can be done in user mode should be done in user mode. So that has an advantage. It means the microkernel is very small. So SEL4 is of the order of 10,000 lines of code, give and take, depending on architecture, etc. And that means any services you build on top are protected by the isolation mechanisms given by the kernel. So you can build servers where their interfaces are guaranteed by SEL4's isolation. So that's really powerful. We get a small kernel, small trusted computing base. Well, it's no longer trusted because it's verified. But yes, the kernel only offers you basic mechanisms. It's really just a very thin wrap around the hardware. And programming on SEL4 is not much different to programming near hardware, naked hardware. In particular, there's none of the application-oriented abstractions you expect from an operating system. So it's BYO file system, memory manager, device drivers, etc. And that's why my other tongue-in-cheek definition of a microkernel, it's the assembly language of operating systems. You really have to do everything yourself. And of course, by and large, people are not able to do that, and we didn't really expect that. But what we did expect was that the community would do the rest for us. We've done the hard work. Now out there go industry, whoever, universities, build operating systems on SEL4 as this trustworthy platform. And it turns out this has not happened. And sort of reflecting back a few years ago, yes, SEL4 is still unrivaled, both in terms of its assurance, but also sort of power, performance, etc. And as such, it remains like the best space to build secure systems on. But the community contributions haven't really gone to the point where we can readily use it. And in the end, that comes down to sort of this assembly language of operating system. It's just too bloody hard to build things on SEL4. You need a lot of really deep expertise. And I naively thought if we have students gone through our advanced operating systems course, that's a small number, but it's in average about 40 a year. That's not a bad base to start with. They have all the skills, the expertise needed to build things on SEL4. It turns out, no, it's not enough. You need actually years and years more work. And so that means out in industry or other universities, etc., there's basically not the skills around for doing this. I'm ashamed to admit, or embarrassed to admit, that we contributed to that as well. because some of the bad designs were actually done in my lab and open sourced. And of course, coming from us, people say, oh, the experts did it, right? So it must be the right way to do it and build on it. And yeah, embarrassing things happened. And then there was the arcane build system you have to use. And the result was train wrecks. So I can't point to any specific ones. No one is keen to talk about their train wrecks, obviously. But I'm aware of multiple projects that started with apparently lots of resources in industry. And after a few years, you don't hear anything about them anymore. And the obvious explanation is this is almost certainly going to be a train or been a train wreck. So my conclusion, and this is what I sort of got to about 3 years ago, is we need an operating system, an actual operating system on SEO4 that's secure, easy to use, and open source. And that hopefully will enable people to really deploy SEO4 on a large scale. Initially, I tried to think, well, this is engineering, shouldn't be done at uni, and it's too big a project anyway. So I've shopped around industry partners, trying to get an industry consortium together. There was some interest, but then sort of the market wasn't hot anymore, and money wasn't that easy to come by, and it didn't go anywhere. But meanwhile, I've done some work with some students, actually a really bright undergraduate student, on really sort of evaluating designs based on SEO4, and came to the conclusion, actually, if you know how to do it, it's not actually that hard. And we can do that with half dozen people in the university. And that's when we started. So this is now Lions OS, which is basically the train wreck stopper, hopefully. That's what it's designed for. So to be more specific about the aims of Lions OS, we want an operating system, and at the moment, we're restricting ourselves to the embedded cyber-physical space. That makes a lot of things much simpler, but also makes it brings the scale down to something where we can really do in the university. But also, there's still plenty of research issues left. It turns out it's not just an engineering project. There's some really interesting research in there. And then the other aims are positive ones. Uncompromising performance, as I said earlier. Security is no excuse for bad performance. And really secure, I want this to be the most secure as ever. And even though we haven't verified almost everything of it, I think it's already a contender for the most secure operating system with ever, just with what we have. But of course, we want to prove that. So the restriction to the cyber-physical space, this is a really important one, because in cyber-physical systems, your hardware resources don't change. They don't come away, go and come, etc. You have a relatively clearly defined system with a really clearly defined mission, and the mission doesn't change overnight. And that allows us to get away with a static architecture. Static architecture means all the components of the system are known at configuration time. That doesn't mean the code that runs in those components is necessarily known. That can change. It can even change on the fly, etc. But the structure is known. So that's the architecture. Obviously, performance means well designed. And after 30 years, I think I understand how to do that. And obviously, we want to verify that. So how do we put that in practice? By using a principled approach. And I really think that you don't have a chance in meeting those goals if you don't strictly stick to some overarching principles. And there's very few of those. So the first one is what I call radical simplicity, which is just a rephrasing of the well-known KISS principles, keep it simple, stupid. That I dug out in Wikipedia, goes back to the US Navy in the 50s, I believe. It's, in my eyes, really one of the best drivers for good engineering design. In the case of Lions OS, this means fine-grained modularity with strict separation of concerns. Of course, this is the sort of stuff we teach our first-year students and never really adhere to. Certainly not in operating systems, but in most other systems I see in the computing world. They do not adhere to this. I believe that is key to actually achieving our goals. And of course, it has a dual purpose. It simplifies the development, very strict modular code, fine-grained modular code with very strict separation of concerns is much easier to implement than complex stuff, but it's also easier to verify. And in general, that goes together, right? If it's easy to implement and to conceptually understand what it does, then that tends to be a good enabler of verification. A more non-standard one is a very clear event-driven programming model. So this simplifies the programming of the system. Every system component in LinesOS is just an event handler. So it gets invoked on a particular event, it does something, and then it goes back to wait for the next event. In particular, this means everything is very strictly single-threaded. There's no internal concurrency in any of the LinesOS components. And the final one is use case specific policies. And this is probably the most radical deviation from standard operating system design, because typical operating systems, they try to aim for some approximation, whether they admit to it explicitly or not, of universal policies. The idea is you have a code base and it will adapt to whatever use case you have. This is a beautiful drive of complexity. Like the Linux scheduler has grown by a factor of 3 in code size over 5 years or something like that, exactly driven by this attempt to adjust to all sorts of use cases. Because when you have something that meant to handle all use cases, sooner or later you get into a pathological case, and then you have to add more code, make it more complex, etc. And this is really behind a lot of the unreliability of real-world systems. But we achieve use case diversity not by blowing out the complexity of our policy implementations, but by making them very easy to swap out. And the other principles help for that. If you have strict fine-grained modularity with strict separation of concerns, and your policy is isolated in a small module, if you need a different policy, you just rewrite that module rather than making it more complex. And this is, again, the assumption of the static architecture, the embedded cyber-physical use case is really something that lets us get away with that. I'm not claiming yet that this will work for general purpose systems. I have a hunch it might, but I'm not making any strong claims at this time. So in other words, it's just the opposite in many ways to the typical Linux, POSIX, and whatever systems, but we can have wrappers around that make it almost look like one. So how does this look? A bit more details. So we have SCL4 running on the hardware, and on top we have our LinesOS, which consists of many components, and this is vastly oversimplified. Because if you see just the Ethernet subsystem has 5 components here, and multiply that by the number of network or interfaces, etc., you get a big number of components very quickly. And of course, the copiers are per client, etc. So there's really lots of components in the system. And the key is their interfaces are enforced by SCL4 enforced isolation. And that means they can be developed, implemented, verified in isolation, and because they are protected from interference by other parts of the system. Just what I said before, static architecture, but that doesn't mean static code. So the code can be replaced, in particular, the policy modules, etc. How does this look like in practice? This is an example of the networking system. So we have a network interface card at one end, and then we have software that controls it, and at the other end, we have clients that use the network. And the network interface is handled by software called the device driver. And we have a very radically simplified module, because radical simplicity, right? Driver model. The driver itself is just an event handler, strictly sequential, etc. And it has separation of concerns, one and only one task. which is to translate between a hardware-specific device interface to a hardware-independent device class interface. So this interface depends on the particular network card. This interface is common to all Ethernet. And so it's just a hardware abstraction. That's all it does. And then, because in general we have multiple clients, we have a component that shares the device between multiple clients, and we call that the virtualizer. And on Ethernet, there is a step we can keep the transmit and receive paths separate. So there is a receive virtualizer, and it presents the one device as multiple virtual devices. It also does the address translation and memory cache management operations, etc. So everything to do with the virtualization bit, basically. And then we have a similar virtualizer for transmit. And this one needs to implement some policy, because if the clients try to overload the network, then the virtualizer somehow has to prioritize the clients according to some policy. And the idea, of course, use case specific policy, you should know what policy you need for your system, and that's hard coded in the virtualizer. There's an ARP for address resolution protocol component for handling broadcasts, so the network discovering where to send things to, etc. And then there is copiers, and they're optional. That whether you need them depends on the security policy of your system. And then there's the client, and the client contains the IP stack. So the protocol stack is not part of the trusted computing base. It's a client library. It cannot break isolation. So from the system point of view, it's not trusted. And we don't care that we have an unverified driver IP stack. We just use LWIP. And every client has its own. And clients can be either native or virtual machines. And again, that's totally transparent to the system. So strict separation of concerns. Now, there's lots of modules, and every packet traverses a lot of modules. And obviously, in order to make that perform, we want to have zero copy operation. So the components communicate via some shared memory where the data lives in a shared memory data region. This is what the device will access with direct memory access. And then there is metadata in a separate region which contains some queues for handling the data. They look very similar to the hardware transmit and receive rings, which are basically pointers to buffers. Ours are a bit simplified, and we separate the packets with valid data from the ones that are ready to be reused, just to simplify things. And that way we hand the packet through without any copying except where needed for security. And everything is very low weight. So, and of course, because these components, remember I said all the Alliance OS components are strictly single-threaded, and we share a device driver by having an explicit virtualizer. That means each of these queues is a single producer, single consumer queue. Again, simplifies implementation massively. And they are separated, synchronized by semaphores, and that's one of the SEO4 mechanisms we use. And because of these, the single-threaded nature of all the components, the only concurrency control that's there is the NQ and DQ functions in those queues. And they're literally three-liners, and you just need to have the memory barrier in the right place. And we have a student working on verifying that, but it's pretty easy to get that bit. So a bit more expanded view of our networking subsystem. Between each of these components, there is this metadata region with a pair of shared queues by which they hand the packets around. Benefit are the components become very simple, and a component doesn't need to know whether the component it communicates with is on the same core or a different one. So the system naturally has a high degree of location transparency. A component can run on any core, and it can be migrated between cores without affecting the rest of the system, except, of course, some temporary latency glitch. So this means we can make up for the loss of concurrency we get by the single-threaded programming model by having a lot of components which we can distribute across cores. And turns out this is a much better model, even from the performance point of view. Can easily reuse Linux legacy drivers. Obviously, a driver or device that's security critical or performance critical, you want to write from scratch according to our simple driver model. But we don't want to write every driver from scratch. So we can just transparently drop in a Linux virtual machine that contains a Linux device driver, and that looks the rest of the system like a native driver. And turns out this is actually a really nice model for developing components as well, because we can use the same setup for developing a LinesOS component in Linux as a user level in one component in one of these driver VMs, and then when it's working, migrate it into LinesOS. And in Linux, of course, we have much better tooling, etc. So compared to Linux, for our IMX8 platform, where we do most of the development, the Linux device driver has 3,000 lines of code, and the total networking system is about 1 million or so. LinesOS, the network driver, 400 lines of code, and literally written by a second-year student. That student wrote that device driver less than 18 months after she wrote the first program ever. Pretty damn smart student, but it shows you writing drivers in this model is not that hard. And I would claim every undergraduate student can do that. IP stack, we could get away with a much simplified IP stack. At the moment, we just use LWIP, which is not necessarily overly performant, but it turns out it does the job. And the whole network system is less than 1,000 lines of code. That's pretty nice. That gives you hope to actually be able to verify it, because these 1,000 lines of code are spread over half a dozen or so components. So the question is, people back since the 80s have this notion that microkernels have performance issues because there's lots of context switches. We take it to the extreme by our fine-grained modularity. That means there's more context switches than in just about any other microkernel-based system. So if there is a performance issue that comes from the microkernel concept, then it would show up here. And networking is actually the best test, because from sort of all the realistic use cases I know, networking will, particularly in the setup we have, will generate the highest number of context switches per second. So it's really the extreme case to test the performance of the system. What do we see? So we use this IMX8 platform. It has a gigabit Ethernet NIC using UDP traffic on a single core configuration. And we apply varying load. So apply a load starting from 0 to up to the 4 gigabits. The NIC is meant to be able to handle. And we measure how much load the system can handle. So we throw packets at it. The client is just an echo that sends it back out to network. And we measure how many packets do we get out. And the green line is LinesOS, nice diagonal, as you would hope for. The received load is equal to the applied load. Linux initially also diagonal, and then plateaus out at about 600 megabits per second. Why is that? If you look at the CPU load used to handle this, we see that the explanation, Linux tops out the CPU at about 600 megabits, and it cannot handle any more traffic. That's why the throughput tops out, whereas LinesOS beats it hands down, achieving the full 600 gigabit throughput with about 65% of CPU load. So roughly about factor of 3 better performance than Linux. For a system that's meant to be very mature and optimized, that's a pretty nice starting point for something written by a bunch of students in a university. It took me a long time to convince myself that these numbers were right. Originally, there was an issue, but then we fixed the performance on our side, and it turns out, as a matter of fact, each time I give this talk, I have to change this slide because the performance has improved further. If we keep going like that, oh no, overhead will go negative. And anyway, I'm pretty pleased with this performance. So people also, so what's behind it? Well, the processing cost per packet in cycles is about, well, almost a factor of 2 better than Linux. Well, that's the best gap, factor of 1.8, and with very low load, very high load, it's about a factor of 3, and it averages out to about a factor of 3. Latencies is what people are interested in. Networks, again, this is small is good, and this is a logarithmic scale. And we see that we beat Linux in latency by factors between 3 and 10. So it's not only less CPU, but it's also handles the package much faster. And that means the performance is comprehensively way above that of Linux, no matter how you look at it. This was single core with multi-core, similar story. Turns out the more cores you give to Linux, the more cycles it wastes. And getting from the single core configuration to the multi-core was a matter of a few days because our system is location transparent, right? You just do a different core allocation. There was some debugging involved, unsurprisingly, but it wasn't a big deal. So why is that? And the explanation is really here. We execute much less code because of our design for simplicity. And that turns out it's not only good for verifiability, it's also good for performance. And we can deploy the system. I've seen in Yuval's lab, there is a system where you tick in when you buy a coffee or something. We have something similar in our lab, this little kiosk where you pay for your purchases. We sponsor the coffee. And of course, this runs on Lions OS. And this is what the Lions OS looks like in this case. So there's about a dozen components. 4 of them are device drivers. If you look at the code sizes, they're all between 100 and about 400 lines, well, 500 lines in the case of the I2C driver. So fine-grained modularity, every module is really small. The total list of modules is here. The red ones are things we don't have to trust because they're inside a trust partition. The trusted bits, part of the TCP, are average of 200 lines of code. So if we can verify anything, then we can verify that. It also runs the SEO4.systems website, and this is what the web server looks like. Similar thing. It uses an NFS client for storage, etc. So how about verification? I've been mentioning that a lot. This is our aim for the next 3 years. That's what we promised Cyberagentur. A system, Lions OS running on RISC-V hardware, where we verify most Lions OS components. We didn't promise to verify all the device drivers, but most of them are pretty simple. Touchscreen will keep using a Linux driver, I assume. We're also working on formalizing the hardware interface, so the interface between the device driver and the actual device, and verifying the device driver against that. We already have verified a high-performance Ethernet driver, but against a high-level abstract spec that doesn't really reflect all the things you need to drive the device correctly. We will be able to do that against the real device implementation, which will also be verified. So our industry partner, Planet 5 in Munich, is working on verifying some critical hardware components on this. And then the ultimate goal is we want to be able to prove that we can confine an untrusted component. So this untrusted component, which gets some sensitive data, is supposed to be able to talk to the rest of the world only via this crypto component and not leak any data through any other channels. And we also have some real-time agenda. So the verification, why I really think this is doable in a time frame, is enabled by the simplicity of the code. So we have the simple event handler, strictly sequential code. We can verify these components using SMT solvers. We've done it already for the network driver. And then we have the inter-module communication, where we have protocols that are mostly, the bugs there are mostly performance bugs. So you try to get avoid unnecessary signaling. And then if you get extreme, then you run into deadlock issues. This is a perfect area for model checking, and we've used that successfully. And so basically, I think we can do a lot of these proofs using automated techniques. And the real research challenges and the composition of these proofs. To me, that's the highest risk of the whole thing. Our formal methods experts are pretty confident about it, so, and I trust them. So how about this confinement thing? As Lambert noted in his famous note many years ago, this requires dealing with covert channels. So this is an untrusted component, so we have to assume it contains a Trojan that tries to leak actively, and we have to prevent any covert channels. As Lambert mentioned over 50 years ago. And, sorry, Lamson, Butler Lamson. SEO4 has already done a bit there in that we verified years ago that it's free of storage channels. But here we worry about timing channels. And the question is, how can we control those? And I'm not interested in algorithmic timing channels. Like if your code has secret dependent execution time, that's your problem. What I'm worried about is breaking the isolation provided by the operating system. So using the microarchitecture to leak data. And the key observation there is we can stop the leak through the microarchitecture if we guarantee that the microarchitecture is never shared between components, or that it's either temporally or spatially partitioned. So temporally partitioned means we get a security domain has access to the microarchitecture, and then when we hand it over to another security domain, we scrub the microarchitecture completely, and then the new domain gets a clean slate, and there is no leakage. Or spatially partition obviously means spatially partition, right? We partition caches. In the case of caches, that's done by cache coloring if the hardware doesn't offer any other mechanisms. And SEO4 by design is actually pretty good for that, because one of the things that makes SEO4 hard to use is that all the resource management is delegated to user level. Basically, the kernel is your problem. This has a nice advantage. If we start off user partitions with completely separate memory pools, then that partitions the kernel memory as well, because in order to do any kernel operation that requires memory, user level has to provide the memory to the kernel. So starting off with partitioned user or colored user memory, we color the kernel memory implicitly. Obviously, there's some kernel data structures that need to be shared. We minimize that by having a separate kernel image for every partition. So this is similar to a multi-kernel approach, where you run a different kernel image on every core and partition the multi-core that way. And then the kernel images, they have to coordinate somehow. We drive this further by, even on a single core, allocating a separate kernel image to each partition. And then there is very little shared state between the kernels. It's a bit more than a page. And we can manage that explicitly by making sure the cache state is deterministic at the context switch. Of course, it's all kernel memory, so the kernel can do that. This is very high level. How does the temporal partition work? Well, this is a very abstract view of a context switch routine. Switch user context basically means copy registers to some holding area and copy the new ones back, reprogram the timer, get back to user. We need to remove any history dependence here. And we do that by flushing any on-course state. The problem is, okay, this flush will depend on the execution history, in particular, how many lines in the data cache are dirty. And so we need to add that to some worst case execution time. And then we need to make sure that anything that's shared is put in a deterministic cache state before we can return. That was a paper where my friend Yuval was a co-author with 6 years ago. And what we realized at the time was it's actually not doable on modern hardware. So in theory, this is all good. In practice, no hardware gives you the right mechanisms, in particular this flush on-course state. There's no off-the-shelf processor that has that. So do we give in? Well, yeah. Turns out it's not hard to fix. And our collaborators at ETH Zurich have shown that by defining a so-called fence.t instruction for the RISC-V architecture, which basically does what we need. So, and in a very principled way. It flushes the D cache, obviously, make sure that everything is consistent. And then it does a complete reset of the circuit of all the flip-flops that are not part of the explicitly architected state. So that's a very safe approach because it means you can't just accidentally miss a few bits, which could be used as a timing channel. They prototyped this on RISC-V processors, both in order, so that's ETH Ariane processor, the CVA6, as well as an out-of-order processor, the C910, and found that expectedly the latency is bounded by the D cache flush. That's the only really expensive operation there. And the hardware cost in terms of additional flip-flops or cheapest state needed is in the noise. How does it work? So this is a channel matrix for an unmitigated D cache channel. So we have different values of a secret and the time to access data on the y-axis. So the channel matrix is the conditional probability of measuring, of observing a certain time given a certain secret. And we see a very strong correlation, unsurprisingly. So this is the unmitigated case. And if we apply the fence.t instruction, it's all gone. Similar, the I cache looks very similar. Again, applying fence.t is gone. History branch table, sort of more messy, but very clearly the channel is gone. And we looked at all the known attacks, and they all get, unsurprisingly, because of this principal design. Unlike other sort of defenses, we can be pretty confident that not Yuval finds a new way to attack this because we really do reset all the flops that are not architected. So, designed 2 publications. So what are we, what's in work here? So we back it verifying that this actually works. So our existing SEO4 proofs get enhanced by adding the cache coloring and the flush in the context switch to the abstract model. The proofs need to be redone and then re-establish the information flow proofs that show that there is an absence, that the confidentiality is maintained. And what enables that is that timing channels, whether something is a timing channel or a storage channel, is really, in a way, a point of view, and that's been pointed out many years ago. In our case, we know that the kind of channels we worry about, the microarchitectural timing channels, they are tied to some hardware state. So they're really storage channels, and we can prove that these storage channels are eliminated. So this is how we can do this without reasoning about time. And I think I'm sort of stretched my welcome here, probably skip over the last 5 minutes. Unless we are not listening about time. Huh? We are not listening about time. Okay. In which case, given that I promised in the abstract, I'll talk about what's more speculative at this sense. So Lines OS, I'm pretty confident about. We really understand how to do that. But as I said, it's aimed at the embedded cyber-physical space. We're also looking at a model for a more general purpose operating system that is provably secure in the sense that it can be proved to enforce a security policy. And we want to be able to enforce a pretty arbitrary security policy, whether it's the classical hierarchical models or more commercial Chinese wall, all this kind of stuff. Any sensible policy should be able to be represented in the system, and we should be able to prove that it adheres to it. The idea of that is, well, obviously, it's a mandatory security policy enforcement. As I said, we want to be able to support pretty arbitrary security policies. And of course, we want to have a minimum trusted computing base that we can at least argue reasonably that it should be possible to verify that. That's the aim for now. And obviously, as I said before, security is no excuse for bad performance. We want to show this actually can be made to work practically. Very high level, this looks like that. There's a bunch of trusted servers at the bottom. So there's a resource manager, a security server, and a connection manager. And then there's a bunch of object servers that provide the actual application-oriented operating system abstractions, file service, network service, whatever. And the idea is a client that gets a new client process that gets started, gets a connection to all the core servers given as part of its initialization protocol. And then when it wants to obtain a service from the system, it wants to invoke an object server. And in order to do that, it needs to send a request to the connection manager and says, I want to talk to this object server. And the connection manager says, okay, I need to check with the security server whether this is a valid operation. And so it sends a message there, gets a response back, security server says, okay, connection server creates a connection and sends that to the client and installs it there. And now the client can talk to the object server. And of course, depending on the security policy, the fact that this client has been allowed to talk to this object server may or may not have an impact on other clients trying to talk to the same object server. That's what the security policy needs to say. And so the implementation of that is that an object server for obtaining for performing a security critical operation. So this is presumably a shared object server that deals with clients of different security domains. It's all easy if you say partition the object servers, obviously. But in general, you want to have shared services. For example, you want to have a file system with controlled sharing enabled. So that needs to be enabled by, provided by the object server. So it will have a policy enforcement module, which it checks with whenever it tries to do a security critical operation. And that policy enforcement module will cache security state. And if it doesn't have a cached security state for a particular operation, it will go back and consult the security server, which has a decision-making component that consults its policy state, which change as a consequence of the operation. And if it says go ahead, then the object server will do that. And one of the core ideas behind making this work for shared services is to have complete control over resource accounting by using resource donation. So we force a client, and this is similar to the basic model provided by SEO4. In SEO4, when you want to perform an operation that requires the kernel to allocate memory, for example, you want to do a mapping operation that requires the kernel to allocate a page table, you need to provide that memory to the kernel. We have a similar model here where we have resource containers. Every process has at least one resource container it uses. And if a client wants to do an operation or requests an operation from an object server that requires resource, then it needs to donate or lend really that resource to the object server. And this is done by having a protocol that allows the resource from the client's resource container to be transferred to the server's resource container. And then the server can use it to hold state or to store the state. And of course, the client has the right to revoke that, but that may end to may then force an end of its engagement with the object server. So that's depending on how the object server operates. At the moment, this is all sketchy, high level, hand wavy, etc. But we are working on a prototype, and I hope within a couple of years to have a much more concrete design of how this works. So I really think it's time for secure operating systems, and I really think we can actually do it now. And certainly for the embedded cyber physical space, I think the Lions OS approach, I think we really understand how to get it right and how to verify it. We promise to do this all within the next 2.5 years, including end-to-end security proofs for the application domain of static architectures. And then the general purpose OS is still more speculative and into the future. So stay tuned here. Thank you very much.